So let us start this question by reading it together so that I can outline the various clues that the examiner has given us in order for them to indicate to us what kind of method they want us to use. And in this question, we are told that one end of a light inextensible string, and while I'm still on the light inextensible string, I want to point out at this particular point that in all questions in M1, which involves strings, the strings will be light and they will be inextensible. There are two things here. Inextensible in the sense that although there is tension in the string, it does not stretch. That is why you are told it is inextensible. Secondly, you're told that it is light. You're told that it is light so that you can ignore its weight in that context. Because in that area where the string is being used, there are probably other weights and other forces which are being used. So the weight of the string itself is so small, we can ignore it. So that is why you will always be told that the string is light and inextensible. So we are told that this string is attached to a ring which is threaded on a fixed horizontal bar. The string is used to pull the ring along the bar at a constant speed. At this point, I want to state that another clue that we've been given here is the idea of constant speed. What is meant by constant speed? Okay, first of all, let me read the rest of it and then I'll come back to that. We are also told that the string makes a constant angle of 30 degrees with the bar and the tension in the string is 5 newtons. In all questions where you are given forces and you are given angles, you will be required to resolve the forces in particular standard directions. The two directions that are there in mechanics 1, there are just two. One of them is horizontal and vertical. The other one is when the forces are on an inclined plane and you are required to resolve along the inclined plane and perpendicular to the inclined plane, as we will see in another question in this paper. So let's see, we are told that this string moves with a constant speed along that bar. I've simulated this motion or animated the motion of this ring to emphasize that tension remains at 30 degrees to the horizontal as the ring moves along the bar. That is why I have animated that. Now, let me go to the idea of constant speed. The reason why we are told that this speed over here is constant. Now, speed is given as distance over time. In other words, when you're given a speed of 0.4 meters per second, it means that this object covers a distance of 0.4 meters in a time of 1 second. So in 2 seconds, it will cover a distance of 0.8 meters. In 3 seconds, it will cover a distance of 1.2 meters, and so forth. How am I getting these distances? This is how I got the first distance. I just added 0.4 onto this one, because the meaning of 0.4 meters per second is that in every 1 second, in a time interval of 1 second, it covers a distance of 0.4 meters. Of course, it is moving in a straight line. So we can say that this is uniform velocity. So that is why I added 0.4 here, because for me to get 2 seconds, I added 1 second onto 1 second. Now for me to get 3 seconds, I added another 1 second onto 2 seconds. So that means I will add 0.4 meters onto 0.8 meters to get 1.2. Alternatively, for me to get 0.8, I multiply 0.4 by 2. For me to get 1.2 meters, I multiply 0.4 by 3. And the distance covered in a time of 10 seconds, you will agree with me that it will be 4 meters. And this will be 10 seconds. What I've done is multiplied 0.4 meters by 10 seconds in order to get that distance. So the distance covered in 10 seconds is 4 meters. Alternatively, I could use this equation here. Distance is equal to the constant speed times the time. And I'm going to get the same distance of 4 meters. You know, 0.4 meters per second multiplied by 10 seconds will give me 0.4 meters. That is why the value of the constant speed is given, or we are told that the speed is constant. Another thing that comes into mind when you're told that the speed is constant is this. Since this object is moving in a straight line with a constant speed, its velocity is uniform. When the velocity of an object is uniform, it means that its acceleration is 0. And when we use F is equals to ma, we find that the resultant force acting on that object is also 0. That means that opposing forces balance out, or they cancel out to give you a resultant force of 0 newtons. All these are ideas which come into my mind because of the mention of the term constant speed. You can see the kind of ideas which I want you to think about when certain things are mentioned in the question. The other thing is this. We are told that this string makes a constant angle of 30 degrees with the bar. When you are given the force and you're given some kind of angle, it is very important that you resolve that force immediately in those two directions, especially if the force given is not in the standard directions. What are the standard directions I'm talking about here? The force is either vertically or horizontally or along the incline or perpendicular to the incline. Those are the standard directions. If the forces are not in those directions, then you're supposed to find the component of that force in those two directions. For instance, here, this force here is neither horizontal nor is it vertical. So I must find its component horizontally. And its component horizontally will be 5 cos 30 degrees. Of course, newtons. Now, how did I get this? The point I want you to remember is this. If you're given a vector and you're given a direction that makes an angle theta with the direction of the vector, for us to find the component of that vector in that new direction, you multiply the magnitude of the vector by the cosine of that angle. In other words, I've been given this force and it acts in this direction. For me to get its component in a direction which makes 30 degrees with its own direction, we must use cos theta. And it's very easy to show this. Otherwise, you just need to recall that. And then immediately you resolve it in that direction, you get the cosine, you resolve in a direction which is perpendicular to that direction, and that is vertically. And that is going to give us 5 sine 30 degrees newtons, like that. Now you find that maybe 5 sine 30 degrees may not be useful to us when it comes to the solution of this question. But it's something that is true. It's a fact. Once you resolve in one direction, you also resolve in a direction which is perpendicular to it. So you will not be penalized for writing something which is true, which is a fact, although it doesn't help you in that particular question. You will not lose any marks. The examiner will just ignore that aspect. And then the last clue here is, of course, we've been asked to calculate work done. The mention of physical quantities. Physical quantities which we study in mechanics or in science usually are defined. To define a physical quantity is to show how it is related to other physical quantities. So the fact that it is mentioned here, I'm supposed to recall its definition in terms of an equation. And this is the equation which comes into mind. I've been asked to calculate the work done. The question I ask myself here is, do I have all the other physical quantities necessary to calculate that physical quantity? Yes. There is the force, there is the distance. The only thing I need to remember here is that this force must be in the same direction as the distance. The distance and the force must be in the same direction. And you can see I've been able to calculate the distance it covers, and I already know the force in that direction. That is why it was important to resolve this force horizontally, because I will get the component of the force in the correct direction. This force and this distance are in the same direction, and that is what gives me the answer of 17.3 Newton meters or joules. And that is how you solve a question like that. Okay, you find that I've spent a significant amount of time here showing you how to arrive at this answer. There is something which I want you to learn. I'm not here just to tell you what the answer is to a particular question. Otherwise, you can just go online and you can find very quickly the answer to that particular question. But most of those places where you get those answers, they don't explain to you how the answer has been arrived at, and they even don't prepare you to answer a similar question in the exam. That's why I find it necessary to spend some time here explaining to you about the clues that the examiner has the habit of giving students, but students are unaware of this. If you find yourself in an exam and you are like, I do not know what to write down, nothing comes into mind as far as this question is concerned. I have had so many students tell me that. I usually know what was missing. They have not been trained to identify the necessary clues in the question. Because the examiners, they are quite generous when they are setting these questions. They always give us clues. And that is why my videos will be slightly longer than usual. So I will appeal for some patience from you, because you will always learn something, even if you feel that I've taken a very long time to answer a particular very simple question. It is not simple. And if you assume it is simple, chances are that there are so many concepts that you are missing. If you're given the same question, for instance here, if they asked you, calculate the frictional force acting on that object, or calculate the work done by the frictional force. You see, it's the same idea, and I've mentioned all those points that are necessary for you to be able to calculate the work done by the friction force. First of all, the friction force will oppose the motion of the object. It will act in that direction. And the frictional force will be equal to the force which is pulling it in this direction. How do I know that? The resultant force on the system is 0, and therefore opposing forces balance out. And if I've got to calculate the work done by the friction force, I'll find that it has a negative sign. Why negative sign? The angle between the friction force and the direction in which it's moving is 180 degrees. So that simple question can be twisted around, and you can be required to calculate so many other things. For instance, even the normal component of the contact force, you can be required to calculate it here. Or even be asked, is that ring making contact with the wire at the bottom part or at the top part? Because that will depend on the weight of the object, rather on the component of this tension, vertically upwards and on the weight of the object before we can determine what is the normal component of the contact force over there. Simple question, but if it is twisted and you're not ready for these clues, then you always get it wrong, or you always find it a little bit difficult. That is the reason why you should listen to every point that I mention when I'm solving the question, whether the question is easy or not. So without further ado, let's go to question 2. So in question 2 over here, we are told that a basket of mass 5 kilograms slides down a slope inclined at 12 degrees to the horizontal. An inclined plane is mentioned here. There is a mass on the inclined plane and the angle that the plane makes with the horizontal is given. So the first thing I would expect you to do is to put down a sketch. Just a simple line is inclined to the horizontal at a certain angle, which is theta. In this case, the theta is 12 degrees. Then we are told that the coefficient of friction between the basket and the slope is 0.2. At the mention of coefficient of friction, I think about frictional force and the way it is related to the normal component of the contact force and the coefficient of friction. Those are the ideas that come into mind. A physical quantity is mentioned and my mind starts working out things which it can remember about that particular physical quantity. So over here we are asked to find the frictional force acting on the basket. So I've already drawn the inclined plane over there. And when you draw the inclined plane, the first thing that you do is to indicate this angle. If it is given in the question, indicate it. If it's not given in the question, probably they will ask you to calculate it. Just call it theta. Allow it to remain as theta like that. And then the other thing is for you to indicate the position of the object, then show its weight. The weight of the object always acts vertically downward, so it will make 90 degrees with any horizontal line that is drawn. The next important point, even before you are asked to calculate anything, is to realize that this weight has got a component which makes 90 degrees with the incline, and the other component is parallel to the incline in such a way that the weight actually appears to be the hypotenuse of this rectangle here. You can see it's along that, with this component being some kind of opposite and this component being the adjacent. Another point that I'd like you to remember is that if you know this angle, you should know this angle. They are exactly the same. And then find the component of the weight in this direction, in which case it takes cosine. You get that vector multiplied by the cosine of that angle. I've just explained that in the previous question. And then the other component, which is perpendicular to this component, takes a sine. And it is in this direction, in such a way that this component of the weight and this component of the weight, they make 90 degrees with each other at this point. Now, they can be treated independently. Those are the things which you do even before you know what the question is asking you, because of something that I've just explained just right now. So you have been asked to calculate frictional force, and when you're given coefficient of friction, you know you must multiply it with the normal component of the contact force. At this point, you want to apologize for that line supposed to be straight and is supposed to be making 90 degrees with the inclined plane. Now, because the object is not accelerating in this direction, this normal component of the contact force must be equal to the opposite force, which is this one. And therefore, I have all the details that are required to calculate the frictional force. So here I've got 50 cos 12. And a use of the calculator will give us 9.78 newtons. How did I know that the friction force acts in this direction? I have to realize that the object is sliding down, so the slope is applying a force on it up the incline. In other words, frictional force tends to oppose the motion of the object. Now let's look at part B. Part B, we are asked to determine whether the speed of the basket is increasing or decreasing. If you calculate this force here, you're going to get a force of 10.4 newtons, the component of the weight down the incline. And the frictional force, which is opposing that, has got a value of 9.78. So you can obviously see that there is a resultant force on this object. If there is a resultant force on an object, if you divide that resultant force by the mass of the object, you will find the acceleration of the object. So this object will have an acceleration. And at that point, the moment you realize that it has an acceleration, which is positive, then you can obviously tell, since it is moving in a straight line, the velocity of the object is changing by virtue of the fact that the magnitude of the velocity is the one which is changing. The magnitude of the velocity is the speed of the object. So the speed of the object must be increasing down the slope. However, we can go right ahead and calculate that acceleration. So you subtract 9.78 over here and divide everything here by 5, and you're going to get a value of 0.124 meters per second squared. This means that the velocity of the object is increasing by 0.124 meters per second every second. And I've already answered that question. The speed of the object is increasing by 0.124 meters per second every second, and therefore it is increasing. And that is how you would tackle that question. Let's go to question 3. So let's look at question 3. In question 3, we are given that two forces, each of magnitude 10 newtons, act at a point O in the directions OA and OB as shown in the diagram. The angle between the forces is theta. The resultant of these two forces as magnitude 12 newtons. So this question is about how to determine the resultant force when you're given a number of forces. This time, two forces which are making a certain angle with each other. We know the steps. Step number 1, connect those forces in such a way that the head of one is connected to the tail of the other. For instance, here, I'm just going to slide one of the forces in such a way that you can see that it goes and makes contact with the head of the other in such a way that its tail is connected to the head of this one. And now I'm going to draw a line from the first tail, because this is the first tail, all the way to the last head over there. This is the resultant force. And we are told that the resultant force has a magnitude of 12 newtons. I could have done that by sliding this one, in which case it would have come here, and the resultant will still be in the same direction. When this force moved from here to here, it moved with its angle, which is theta. Remember, this was the angle theta. That angle has come here. At this point, let me mention that I have had a number of students who usually think that just by drawing a line from this point to this point, they are finding the resultant. It is not the resultant, because first of all, the two forces that you're combining are connected tail to tail. That is unacceptable. So the first point is to ensure that the two forces that you're adding are connected in such a way that the head of one is connected to the tail of the other. And then draw a line from the first tail, that is at the beginning, all the way to the last head, that is where all the forces stop. The direction which points from the first tail to the last head is the direction of the resultant vector or the resultant force. And then the length of that arrow is proportional to the magnitude of the resultant force. However, over here, I've just drawn sketches without considering the scale because I want to calculate that force. When you look at this triangle, because now I've got a right-angled triangle, we can call this right-angled triangle, we can call this point A, and the opposite, and therefore this angle is A, and the opposite side to that angle, we give it the value A, and that value is 10 newtons. This is B, and this angle here, I'm going to call it angle beta, because I know beta plus theta will give me 180 degrees. In other words, theta can be obtained by subtracting beta from 180 degrees. That is why I want to calculate angle beta. That angle, the side which is opposite to it is B, and its value is this. While this angle here, or okay, this point here, the apex is C, this angle is C, and this length is C, and its value is this. At this point, I have a triangle with all the sides known, rather, they are given, and I'm required to calculate an unknown angle. Definitely, it is at this point that I use the cosine rule. And because I'm interested in this angle, by the way, angle beta is the same as angle B. I've just replaced it with this symbol there. So don't get confused. Where B and beta, they are coming from. They are one and the same thing. So because I'm interested in this angle, I should use side B. So I'm going to say B squared is going to be equal to the other two sides, A squared plus C squared minus 2 times A times C, and then cos of beta, cos of that angle. Substitution, this will be 12 squared, this is 10 squared, there's another 10 squared, this is 2 times 10 times 10, and then I have cos beta. If you work out this, you're going to get angle beta is equal to 73.7 degrees. And then you will quickly come over here. In order to find theta, you will do 180 minus 73.7, and you're going to get 106.3 degrees. And that is how you get an angle like that. The point I want you to get from here is for you to be able to find the resultant force, you must connect the two forces head to tail. That is in a situation where you have a system of forces and they are shown in a sketch. Chances are that they want you to use that method. If that is not the case, then you can get the resultant force using F is equals to ma. But I don't see anything here which suggests the use of F is equals to ma. Okay, part B requires you to find the component of that resultant in this direction, in the direction OA, because this is point O, A is here, this is O, and B is here. Okay, there is a conflict of symbols here because I named this triangle to have the apex A, B, C, not considering that this point was originally referred to as point O. But I hope that is not confusing to you. So I want to find the resultant force, the component of the resultant in the direction X or in the direction OA. And if I know this angle here, I know this angle as 106.3, this is what I will do. One of the components of the resultant is 10 newtons. I mean, the horizontal component consists of these 10 newtons to start with. And then I'm going to resolve this 10 newtons here because it was originally here. I'm going to do that 10 newtons cos of this angle. So I'm going to add 10 cos of 106.3. And this will be 10 plus, this will have a negative sign because this angle is obviously greater than 90 degrees and it has a value of 3.3. And over there you're going to get, let me just check the answer because I had already worked it out. Actually, this value here is the 3.4, so that you get 6.6 newtons. That's how you work out that. Alternatively, is to get this angle here, you can refer to it as alpha, and you're going to get the component of the resultant in the direction OA is going to be equal to the resultant force itself, which is now 12 newtons cos of alpha. Maybe you can verify this is equal to this value later on, because you can get alpha by doing sine alpha over 10 is equal to sine beta over 12. I'm using the sine rule there. Sine alpha, see alpha here, divide by the opposite side, which is 10, is equal to sine beta, which we know, I know beta is 73.7 divided by 12. And you can see the only unknown is alpha, and I can be able to get alpha. Once I get alpha, I come and do 12 cos alpha will give me the resultant force. And you'll find that it gives you the same value of 6.6 newtons. And again, you can see that question is just as simple as that. Let's go to question 4. Now, the question in question 4, we are told that a box of mass 4.5 kilograms is pulled at a constant speed of 2 meters per second along a rough floor by a horizontal force of magnitude 15 newtons. A lot of information has been given there. You've been given that there is a box, mass 4.5 kg. It's moving with a constant speed, and we know what comes into mind when the constant speed is mentioned. Acceleration is 0. We can be able to work out the distance by doing speed times the time. And the horizontal force which is pulling it is 15 newtons. And yet we know that the resultant force on the system is 0, and there is a force acting to the right of 15 newtons. In fact, let's look at the diagram of that. And here I've already drawn the diagram. So this is what we have. There is this pulling force of 15 newtons. And this object has got a speed of 2 meters per second to the right. This object has got a mass of 45 kilograms, so its weight is, 4.5 kilograms, so its weight is 45 newtons. And we know that there is the value of the normal component of the contact force, which should be equal to this, because in this direction, the resultant force is 0. Now, because the acceleration over here is 0, by virtue of the fact that the speed is constant and it's moving in a straight line, A is 0, it means that the resultant force is 0, meaning that if we know one of the forces acting in this direction, we should know the force which opposes that, which is friction force. And it should have the same value of 15 newtons for the resultant force in that direction to be 0. You see the argument? Now let's look at the question. Find the coefficient of friction between the box and the floor. It's very easy. Coefficient of friction, mu, is given by frictional force divided by the normal component of the contact force. The friction force is 15 newtons. That normal component of the contact force is 45 newtons. And here I get a third, which is 0.33 recurring. Very simple. You see, when they give you clues in the question, I hope you're following how I'm identifying these clues as I go along. Notice that I'm not leaving anything to chance. Yeah. Then we are told that the horizontal pulling force is now removed. Find the deceleration of the box in the subsequent motion. And that is what we have here. Now we have removed this force. By the way, the friction force will still have the same value of 15 newtons. It's the driving force that has been removed. And now I want to work out this acceleration. Notice how the examiner states it. Work out the deceleration. But when it comes to using equations, there is nothing like deceleration. Everything is acceleration. So always work out the acceleration. It will have a negative sign, and then state that value that you got, this time without the negative sign, and you will have stated the deceleration. This is what we mean. A is given by the resultant force divided by the mass. We are resolving to the right. The force acting to the right is obviously 0. There is no force. Subtract the force which is opposing it, which is 15. And of course, divide by the mass, which is 4.5. This should give us negative 15, 150 rather, multiply by 10 there, multiply by 10 over here. I divide by 45, and that should give us a value of, let me see the value that I got. I got a value of minus 3.3 meters per second squared. Minus 3.3 meters per second squared. So when it comes to stating the deceleration, I will state that the deceleration is 3.3 meters per second squared. And you can see I have ignored the negative sign because I have referred to that acceleration as a deceleration. And that is what you should always do. Let's look at part 3. The distance traveled by the box from the instant the horizontal force is removed until the box comes to rest. Of course, now I have so much information. I've got the acceleration. I've got the initial speed is 2 meters per second, because when the force is removed, it is moving with the 2, and the final velocity is 0. Notice that no time has been mentioned. If that is the case, then I always think about the equation that does not have time in kinematics. Over there, the distance is s. So s will be given by v squared minus u squared over 2a. v is 0. Over here, I've got the u is 2 squared. 2 squared is 4 divided by 2 times minus 3.3. The denominator will carry a negative sign. The numerator has a negative sign. Those two negative signs will cancel out and they will give me a positive value. That value, according to me, is 0.61 meters. And that is for how far it will travel when that force is removed. Now let's look at the next question, which is question 5. As usual, let's read the question together. A cyclist travels in a straight line from A to B with a constant acceleration of 0.06 meters per second squared. Constant acceleration? The resultant force is constant. And first of all, there must be a resultant force for there to be an acceleration. And it must be constant by virtue of the fact that the acceleration is constant. His speed at A is 3 meters per second and his speed at B is 6 meters per second. Find the time taken by the cyclist to travel from A to B. I think if I'm given A, U, and V, to get T, I just need to use one of the equations of, no, I think that one will be relevant in part B. Over here, this is U. This one here is U. This is V. This is U. And this is A. You see, the moment they give me this and they're simply asking me to get T, I go to the definition of acceleration. And acceleration is given by V minus U over T, which implies that T must be V minus U over A. Very simple. So our T will be V, which is 6 minus 3 divided by 0.06. And this is like 300 divided by 6, which will give me 50 seconds S there. And then the next part is to calculate the distance AB. The distance AB can be obtained using an equation such as V squared is equals to U squared plus 2AS, in which case S will be V squared minus U squared over 2A. The V is 6, so 6 squared is 36. U is 3, 3 squared is 9. Divide by 2 times 0.06. And when you manipulate this, you're going to get a distance of, I think, 225. You can confirm that. Let us just confirm that. Or maybe I had worked it out somewhere around here. Yes, the distance will be 225. And it appears as if I used a different equation, which is S is equals to UT plus a half AT squared, which will give you the same value of 225 meters. That is the distance from A to B. That is the vector, but its magnitude is that much. Because of course it is moving in a straight line. Now in part B, we are told that a car leaves A at the same instant as the cyclist. In fact, they leave at the same instant. As the cyclist is leaving, the car is also leaving, but the car is traveling differently. The car starts from rest. So, as far as the car is concerned, U is 0. Notice the equation. Starts from rest means that the initial velocity is 0 and travels in the same straight line to B. The car reaches B at the same instant as the cyclist. What they are telling me is they took the same amount of time to cover the distance AB. And because I know the time that was taken by the cyclist, I know the time that the car has taken. At time t seconds after leaving A, the speed of the car is kt squared meters per second, where k is a constant. When I look at this, I can see that the velocity of the car is a function of time, and it's given by kt squared. When I'm given either the velocity or the acceleration to be a function of time, I usually know that some differentiation and integration is involved. Like for instance, for them to get the velocity to be equal to kt squared, somebody must have differentiated the displacement with respect to time. And this is the equation which is required here, because I'm required to calculate the value of k. So if I separate the variables, I'm going to have ds is going to be equal to kt squared dt. And if I integrate ds with respect to s, and this with respect to dt, with the limits of integration from 0 all the way to 50, I'm going to get a total distance of 225. So if I integrate over here, I'm going to get k is a constant. This one becomes t. I increase the power by 3. I divide by the same power, and then I put the limits of integration over here. 0, 50 is equals to 225. And a manipulation of this will give me the value of k, hoping that you understand how this one is done. If there is a problem, this is what it means. K is a constant, but these are the two values of t. So you will introduce t here. You will have 50 cubed divided by 3 multiplied by k minus, we introduce 0 here, it makes the whole thing to be 0. So the only expression you're going to have is 50 cubed divided by 3 times k is equals to 25. And then you make k the subject. And that value of k will be, I got the value of k to be 3 over 5,000. I will leave it as a fraction, 3 over 5,000, because by the way, it is a constant. And then from there, I'm required to calculate the speed of the car at point B. The equation for calculating the speed is given here. So let me, first of all, clear some space so that I can be able to show you how I get that velocity. I've just been able to show that the velocity as a function of time is given by the value of k, which is 3 over 5,000 t cubed. I mean t squared. But the value of t is 50. So v, when t is 50, is going to be equal to 3 over 5,000, sorry for that, times 50 cubed. And a manipulation of that will give me a velocity of, I got 25 meters per second. You can verify these values per second. Again, that is how you would calculate a question which requires the use of differentiation and integration, simple integration. What we learn here is, if you see that the velocity or the acceleration is expressed as a function of time, then you will know that either you will be required to differentiate or integrate. And you know, we always move from displacement to velocity to acceleration. That is, when we integrate the previous value, we get this value. If you differentiate displacement with respect to time, you get velocity. If you differentiate velocity with respect to time, you get acceleration. Now the opposite is true. If you integrate velocity with respect to time, you get, acceleration with respect to time, you get velocity. You integrate velocity with respect to time, you get displacement. And that is what we did there. Now, what prompted me to integrate is because I already know the displacement. If I knew some kind of an acceleration of the car and its function, I would be able to integrate the acceleration and get the velocity at particular time intervals. However, we are going to encounter more of this in subsequent papers. In this question, you can see that the question on differentiation and integration was so straightforward. But remember to follow every step that I follow here. You can skip some of those steps in the exam because by then you will have known some of the things which I'm doing here. So although I know most of these things, I'm not skipping them because I know you might just require that particular step. That particular step may be the one which has made that question a bit difficult for you. And if I skip it, I'll not be helping you. So, having said that, let's move over to question 6. This question is on energy, work, and power. How do I recognize that? It is just from the information given. Just by scanning, when you get a question paper and you look at it, sometimes you just scan looking for certain physical quantities. And when I look at it like this, I can see energy somewhere. The moment I see energy, I see work done, I know this one is a done deal because I know everything about energy, work, and power. Just pay close attention to see how these things unfold. We are given a lorry of mass 1500 kg climbs a straight hill of length 800 meters. I'm getting an idea of an inclined plane, and of course the hill is inclined at 2 angles to the horizontal, so I know there is a certain angle over there. For P's journey from the bottom of the hill to the top, find the gain in gravitational potential energy, mgh. If I know that, if I know m, I know g, those two I know. Do I know the h? Of course, I know that h is the vertical height covered. So it must be the opposite of that triangle. When you draw an inclined plane, there is always the horizontal, there is the incline, which is the hypotenuse, and then there is this height. This height is what is required there. And I can get it because the hypotenuse is given is 800 meters. The angle is given, I can get the opposite. By doing sine of 12 is going to be equal to h over 800, and then I use mgh to get the gravitational potential energy there. So that one is very easy. Let's look at the work done by the driving force. Look at it. They state it so clearly. Work done by the driving force. In my course, Mechanics 1, I have expressed these terms over and over again. So if you have gone through that course, you know the importance that I place on this aspect of talking about forces. And maybe when you talk about a force doing work, you must identify the work done by the force and on which object, because forces are exerted by something else on something else. They don't just exist just like that. The examiner follows the same pattern. The work done by the driving force. And the driving force has a magnitude of 7,000 newtons. Of course, the driving force must be along the incline. So if I know the distance moved is 800 meters, and I know 7,000 newtons is the driving force, I can use work done is equals to force times distance to get that. And of course, now in part C, I can combine the work done because I'm required to calculate the work done against the force resisting the motion. So let's see how we work out part A, because I think I've spent quite some time talking about it, but I think it is worthwhile talking about it. before I start inking, I'll first of all want to put away that second part so that I can have some space here where I can draw that incline. See the incline here, the angle is here. The height I was talking about is this one here, which is this. So for me to get that h, I will do sine of 12 is going to be equal to opposite of the triangle over the hypotenuse, which is 800 meters. And you can see obviously h is 800 sine 12. That is what I need in order to calculate E, potential, gravitational potential energy, which is mgh. The mass is 15,000, g is 10, h is 800 sine 12. And over here, I got a value of, let me just see where I worked it out. Approximately 4.2, it's rounded up by 10 raised to power 6 joules. That is for part A. Part B, which is the work done by the driving force. I'm using those symbols. It's the same symbols I've used in my course. It's going to be equal to the driving force itself times the distance moved by the driving force. And this one will be 7,000 times 800. And I got 5.6 by 10 raised to power 6 joules. And now when it comes to calculating the work done against the force resisting the motion, I use the principle of conservation of energy. What does it state? It states that the work done by the external forces is equal to gain in energy of that system, the gain in the mechanical energy of that system. What are these two external forces? The two external forces are the driving force and the frictional force. So remember, the frictional force, the force resisting the motion, must be acting down the incline. How do I know that? I know that the lorry is moving up the incline. And the force which is resisting the motion must of course be acting in the opposite direction. So, but the distance moved by that frictional force makes an angle of 180 degrees with it. So let's see how this one unfolds. The work done by the driving force plus work done by resistance is equals to gain in potential energy plus gain in kinetic energy. I'm going to rule out kinetic energy because it has a steady speed. I ruled that one out because the change in speed is 0, therefore its kinetic energy does not change. So I ruled that one out. And you see, I've got all these values. This is 5.6 by 10 raised to power 6. Work done by the friction force is negative. Let me leave it as work done by friction, just like that. It's going to be equal to gain in potential energy, which is 4.8 by 10 raised to power 6. And of course, over here, I'm going to rearrange this, and you'll find that the work done by the frictional force, of course, it will be 4.8 minus 5.6, everything by 10 raised to power 6. And when I do that, 5.6 minus, let me see whether I worked it out. Let me confirm using my calculator because I can see that is where I reached. It will be 4.8 minus 5.6, and I get minus 0.8. Minus 0.8 by 10 raised to power 6 joules. It's a bit messy because of the space, but I hope you're following. The negative sign is because of the way I have defined this. This is work done by friction force. And because the distance and the friction force are in opposite directions, I expect the negative sign to come in. So when I state it the way the examiner wants, work done against, that's why I underlined that. I will forget about the negative sign and say it is 0.8 by 10 raised to power 6 joules. It's just as simple as that. Let's go to part 2 of the same question. So in part 2 of the same question, you are told that a second lorry Q also has the same mass of 1500 kg and climbs the same hill as P. The motion of Q is subject to a constant resisting force of magnitude 900 newtons. So this force over here is 900 newtons. This one. You can say it is the force, resistance force, 900 newtons. So we can calculate the work done against the resistance. And Q's speed falls from 20 at the bottom of the hill to 10 at the top of the hill. So there is some change in kinetic energy. Change in EK. In other words, gain in kinetic energy is a half times 15,000 into V squared, and V is 10 squared minus 20 squared. You can see the appearance of a negative sign over there. So this gives me 7,500 times, into brackets I have 100 minus 400, that is like minus 300, and I'm going to get minus 2.25 minus 2.25 by 10 raised to power 6 joules. That is the gain in kinetic energy. So if I call it loss in kinetic energy, I will forget about the negative sign. But I wanted to keep it as gain in kinetic energy so that it can fit into that magical expression. That expression never fails to work. It never fails to work. The expression that I've just used in the previous question. Okay, let's see what we've been asked to calculate. Find the work done by the driving force as Q climbs from the bottom of the hill to the top. By the way, all the other factors, they are known. Work done by frictional force is going to be equal to the frictional force times the distance moved by the frictional force. And this one will be 900 newtons times the distance moved is 800. And there is a negative sign here because there will be cos 180 degrees because that is the angle which separates them. And that one is going to give me cos 180 is minus 1, so I'm going to forget about that. But 900 times 800 will give me, I want to keep it to the same power, 1, 2, 3, 4, 5, 6, 0.72. There's a negative sign by 10 raised to power 6 joules. And remember, the gain in potential energy remains the same. How much was it? It was 4.2 by 10 raised to power 6 joules. You can see the only thing which is missing here is the work done by the driving force, because that relationship usually has three components: work done by driving, work done by friction, work done by external forces on one side, gain in energies on the other side. I like to separate it that way because it makes the solution to be so beautiful. Gain in kinetic energy. So it is this one that I want. So I'm just going to say work done by driving is going to be equal to potential energy. Now I'm going to just deal with powers, because I deal with these numbers. 4.2, it will be over there. Gain in kinetic has a negative sign, so plus negative 2.25. And then work done by friction, it is on this side and it has a negative sign. It goes to the other side, it will have a positive sign, 0.72. So I'm going to have 4.2 minus 2.25 plus 0.72. Everything over there raised to power 6. So 2.67 by 10 raised to power 6 joules. So beautiful. This question has got so many words, but if you just follow my method in such a way, when you meet a physical quantity, what does it trigger in your mind? If you follow that method, you will start enjoying mechanics. Let's go to the last question, which is question number 6, a very interesting question. We are in question number 7, where we are given particles A and B of mass, say 0.15 kg and 0.25 kg respectively. That is, A has got the smaller mass, B has got the bigger mass, are attached to the ends of a light inextensible string. I've already explained the meaning of inextensible string in question 1, which passes over smooth pulley. The mention of the word smooth means that there is no friction force, there is no resistance. The system is held at rest with a string taut, that is tight, and with A and B at the same horizontal level as shown in the diagram. The system is then released. In such a situation, usually expect that the bigger mass is going to pull up the smaller mass. In other words, B will move down while A moves up. Find the downward acceleration of B. And then after 2 seconds, B hits the floor and comes to rest without rebounding. The string becomes slack, that is, it buckles, and A moves freely under gravity. Let me just use a piece of thread to explain what it means by something buckling. So this is a piece of thread. Assume this is a piece of thread. It's tight, it's taut. When it becomes slack, that is what happens. When it becomes slack, okay? Find the time that elapses until the string becomes taut again, and then sketch on a single diagram the velocity time graph for both particles for the period from their release until the instant that B starts to move up again. Now, in order for you to be able to understand this situation, because this situation is very unique, I have had a number of students asking me about this question, but the moment they saw the simulation, they saw it from a different angle altogether. That is why I created this simulation. So watch what will happen to the masses when I press enter. You see what happens? Let me repeat once again. B moves down, hits the floor, but A continues, the string becomes slack, it reaches maximum height, and then comes back to that particular position, where B is just about now to move up. In different questions or in different years, you would be given a particular system like that, and then you're required to calculate the forces acting on B. So it is important to study this question in details. So let me go to this one here. It is, by the way, it is the same simulation. It's only that now I've created some more space, and now I want it to move slowly. Hit there, continues to move, and then falls back to that point. What was the first question? It's about the acceleration of the block. When the system is in that particular position, when A was here, let's assume that A is here now, and B is somewhere around here, and there is a force acting on B, which is its own weight, and its weight is mg, and that will be 2.5 newtons. The weight of this other one is 1.5 newtons. There is tension in this string like that, and over here like that. B is accelerating downwards, A is accelerating upwards, A. So I'm going to use F is equals to ma for A. So for mass A, a resultant force is equals to ma. I'm going to resolve upwards. When I resolve upwards and use F is equals to ma, I will realize that the resultant force on A is T minus 1.5 is equals to 0.15 A. When it comes to B, it will be the other way around, 2.5 minus T, because now I'm resolving downwards, 0.25 A. And it's always a very easy situation where you form these two equations and then you add them downwards in order to solve them simultaneously. When you add, this T and this T will cancel out with that. This and this will give you 1.0. And when you add everything to the right, it will give me 0.40A. And you can see A is 1 over 0.4. And this is what is giving us 2.5 meters per second squared. That is the acceleration with which these masses are moving. So B is accelerating downwards with the 2.5 meters per second squared. A is accelerating upwards with the same amount of the acceleration. So we have found the downward acceleration to be 2.5 meters per second squared. After 2 seconds, B hits the floor and comes to rest without a rebounding. The string becomes slack, and A moves freely under gravity. We have already seen this. Find the time that elapses until the string becomes taut again. How much time is going to elapse? In this one, I've created some distances so that you can be able to see what is happening. Again, I play the same simulation. I want you to watch this point here, there, and then it comes here. Let me play the simulation once again because I want you to get that very clearly. Watch A. As soon as it reaches this point, we start timing. All right? We start timing so that it moves, reaches maximum height, and then falls back here. That is the time that we have been asked to calculate. The time that elapses from the point when the string becomes taut, becomes slack, until it becomes taut again. Those are the points which are missing when you have some difficulties here. Okay, let's look at that. The time required is from that point, the string is slack, it becomes taut again. That time, that way and that way. Let's see how you would work out that particular part. So for one thing, I can do it in two ways. I can get the velocity it has here upwards, the u it has, and then the v it has at that point, and then multiply that by 2. And perhaps that is what I'm going to use now. Now, I know that the acceleration of b downwards, like that, is 2.5. Just worked out this. So I want to calculate the speed that it has just before it hits the ground, using u is equals to v is equals to u plus at. A is 2.5, t is 2, and that is 5 meters per second. So the speed b has just before it hits the ground is 5 meters per second. Now this is the trick. A has the same speed as 5 meters per second because the string is inextensible. So the u for A is 5 meters per second upwards. And then when it reaches maximum height, the v is 0. How much is the acceleration of A upwards for this motion? It is not 2.5, it is 10. Actually, minus is equals to minus g, which is of course minus 10 meters per second squared. Because when the string becomes slack, the object is now moving under gravity. So for me to get t, I just need to get v minus u over a. V is 0, u is 5, a is minus 10. And this becomes 0.5 seconds. But remember, it takes the same amount of time to fall downwards. So you add that. So t total is 0.5 plus another 0.5, which will give us 1 second. The other method that I can use here is this one. S is equals to ut plus a half at squared. For A, the total displacement will be 0 because it moves from here and comes back to the point where it started. U was 5, t I do not know, plus a half, and because it's moving upwards, minus 10 is the A, and there is the t here. This one is going to be equal to 5t minus 5t squared. If I factor out 5t, I remain with 1 minus t. And here, I know either t is equals to 0 when the displacement is 0. Of course, that is true because just before it starts its motion, displacement is 0. When t is 0, displacement is 0. So this one is a correct answer. And then, or t is equal to 1 second. After 1 second, again, the displacement becomes 0 because it comes back to the starting point. That's how you get those times. However, I've given you two methods of working out the same. Now, let us look at how we put this on a graph. This is the kind of graph that we have for motion A and B. I'm going to take the motion for B downwards to be positive. I want to do that because when the object is moving downwards under gravity, the value of g will always be positive. Now, for the first 2 seconds, the velocity of B starts from 0 and rises to 5 meters per second. Then when it hits the ground, its velocity becomes 0 immediately and remains so while the other one is still moving. And the other one takes how long? 1 second to move that extra distance and then fall back. So this is 3 seconds. How is A moving? A is moving in the opposite direction. And remember, this is velocity. That is why there is part of the velocity is positive, another one is negative. Downwards velocity is positive, upwards velocity negative. And it, of course, it takes 2 seconds for its velocity to rise to -3. I mean -5, sorry. It's equal in magnitude to the velocity of B, but in the opposite direction. Now, for the next 1 second, it moves under gravity. So its velocity reduces from -5 to 0 in a time of 0.5 seconds. So this is 2.5. This one here. 2 plus 0.5, 2.5. And then it doesn't stop at maximum height. At this point, the object is at maximum height. And then it falls back, where the string becomes taut again. And when it comes back to that point, it comes back with the speed with which it left. It left with 5, it must come back with 5. You know, when it's moving upwards, its velocity is -5. When it comes back, its velocity is +5. That is why, for B, -5, +5. And all that takes place in 1 second. So when it comes back to the point when the string becomes taut again, it's after 1 second. Again, this is 3 seconds. So both of them take 3 seconds and their motions end there. And that is how you would tackle the entire paper. So I want to thank you very much for your patience through the entire paper.